Let's talk about crystal field theory. We're going to start with the octahedral shape, and altogether we're going to look at three specific shapes: the octahedral shape, the square planar shape, and the tetrahedral. But let's start with the octahedral shape first. Okay, the idea within crystal field theory is that for any transition metal that you have, you're going to have a set of 5 d orbitals, right? You have your dxy, your dxz, your dz squared, dyz, dx squared minus y squared. Those are the 5 sets of the orbitals, and each one of them has a specific shape associated with it and a specific direction in space where it is oriented. And depending on which transition metal you have and what the charge of the transition metal is, you're going to have an X number of electrons present in your diagram. And just to remind you, when you're filling diagrams like this, you first add 1 electron per box as long as the boxes are of the same energy. And once every box has been filled completely with just 1 electron, that's when you come back and start pairing them up. Alright, altogether we call these the degenerate orbitals, orbitals that have the same energy overall. But then the question arises as to what happens to the d orbitals when you create a coordination complex. And the idea right here is that the coordinated covalent bond that's formed between the ligand and the metal center is one via lone pairs of electrons sort of being donated from the ligand to the transition metal. So in essence, the ligand is adding electron density to the metal. And because the d orbitals can technically be the places where the electrons are housed within the transition metal, this creates an electron-electron repulsion. And ultimately what happens is that for the octahedral complex, you end up raising the energy specifically of the dc square and the dx square minus y square orbitals. At the same time, you can leave the xy, xz, xc at the same level as the original d orbitals, so they could be dropped down in energy. Now the idea I'm going to show you in a second derives from the symmetry argument of where the ligands are located in relation to the d orbitals themselves. But the energy separation between the 3 d orbitals on the bottom and the 2 on the top is what we call delta octahedral, also known as the crystal field splitting energy of the subset right here. And the 3 on the bottom represent a set of degenerate orbitals, whereas the 2 on top represent a different degenerate set of orbitals, right? They are the same energy as each other, but they are not the same energy as the 3 on the bottom, hence the fact that we're drawing them farther up in the drawing. Alright, now to kind of explain to you why this happens, you have to consider how the d orbitals are interacting with the ligands as they are present in their 3D space. So the dyz orbital, the one that goes left and right and up and down, if you think about that particular orbital in relation to the positions of all the different ligands in the octahedral complex, what you're going to see is that the interaction is very minimal. In fact, the places where the ligands are binding happen to be right where the nodes of the d orbitals are present. So technically speaking, adding electrons to that particular volume of space presents no problem because those are technically the nodes of the d orbital. You're not going to have electrons there to begin with. The same thing is true for the dxy orbital, because you have all of the L ligands in the equatorial plane of that octahedral complex located right in between the orbitals and only connecting right at the node. Same idea is presented for the dxz orbital, where the apical ligands, top and bottom ligands, are basically right in the middle of the 2 lobes of the d orbitals, only connecting right at the nodes. So they have minimal interaction with the d orbitals, this particular 3. And so they remain, undisturbed. But then you look at the dx square minus y square, and what happens now is that the equatorial ligands, the 4 ligands here coming at the front and the back of the complex, are actually in direct contact with each one of the lobes in the dx square minus y square orbital. And the same is true for the dz square orbital. The ligands in the apical positions are in direct contact with those particular orbitals. So now the idea is that if you are to place electrons in the dx square minus y square or the dz square orbitals, because those electrons that pertain to the metal center are now going to be in direct contact with electrons that come from the ligand, you're going to have electron-electron repulsion, and as a result, these two orbitals will lie higher in energy than the bottom three. Alright, now let's take a look at the square planar situation and see if we can, come up with some analogs to the octahedral structure. Alright, so once again, if you have the naked metal center, you're going to have 5 degenerate orbitals. But when you form the square planar geometry, now you have 4 ligands that are present in this equatorial plane of the metal complex. And ultimately, the splitting diagram that you get is the following one. You have 2 on the bottom, 1 slightly higher in energy, a second one a little bit higher in energy, and then you have the dx squared minus x, dx squared minus y squared orbital all the way up. And this is actually the biggest increase in energy. And the separation between the last orbital that contains electrons and the very last one that doesn't have any electrons is what we call the delta square planar splitting diagram, which happens to be roughly the same as the octahedral one. Alright, now to explain this peculiar shape of the d orbitals, you have to consider the square planar shape in relation to the d orbitals. Alright, so the dxc, if you look at what's going on here, there's minimal interaction. The only interaction happens right at the node, which is the place where you will not have electrons within that d orbital, so that's okay. The same thing can be said about the dxc orbital. The interaction happens only at the nodes. There's really no interaction with the lobes themselves, so the interaction is minimal. But when you look at the dxy orbital, now you have some interaction, not as great as we're going to see for the rest of the orbitals, but because the L ligands are lying, in between the particular lobes, and as it turns out, the shape of, the bond lengths of the metal to ligand complexes are actually shorter than the octahedral complex. So there is a slightly higher interaction here, not a lot more than what we see down here for the dyx and the dx. What am I saying? The dyz and the dxc orbitals, but it is a little bit higher nonetheless. The DC square, here you can see clearly that yes, all 4 of those ligands are interacting with the donut segment of the DC square orbital, so there is a direct contact with the lobes, making it higher in energy. And the dx square minus y square is by far the worst out of all of them, because each one of the lobes of that orbital are in direct contact with all 4 of the ligands found in the square planar shape. Now another way to look at it, and kind of helps out also to kind of derive the square planar shape, is to think of the octahedral shape and the splitting diagram of the octahedral complex, and then look at what happens when you remove the 2 ligands in the apical positions. Basically, we take that ligand and elongate it until it's finally no longer there, and do the same thing with the apical site on the bottom portion of the complex. Eventually, you derive the square planar structure. And the idea right here is that as the ligands on the top and bottom trajectories of the octahedral complex are removed, the repulsive interaction with the dc square orbital gets lower, it diminishes. And if you look carefully, your dc square orbital that was up here now gets dropped in energy. However, as you remove the ligands from the apical site, the bond length of these equatorial ligands decreases, because now they have more room, so they can actually get closer to the metal center. And by doing so, they make the interaction with the dx square y square orbital even worse than it was before in the octahedral structure. So now that orbital gets raised in energy. And the same thing can be said for the 3 orbitals down here. The interaction with the dxc, dyc gets lowered a little bit more because you don't have the extra 2 orbitals, the extra 2 ligands present. The dxy orbital, it's a little bit worse than what it was before, but not a lot more. And as I said, the dc square orbital gets dropped down energy because you have removed the two orbitals that were in direct contact with it before, whereas the dx square minus y square gets raised in energy as a result of the shortening of the bond length. Alright, now to finish up this analysis, let's talk about the tetrahedral structure. The tetrahedral structure, as you may recall, looks as follows. Remember that the dash bonds represent bonds pointing away into the screen of your computer, whereas the ball bonds represent ligands that are pointing towards you, coming out of the screen. The splitting diagram is actually the opposite of that of the octahedral. You have 2 on the bottom, the dc square and the dx square minus y square, and you have 3 on top, which is exactly the same type of orbitals you have for the octahedral structure, except that now the order is reversed. And the reason this happens is because of the same considerations we had before. If you look at the octahedral structure in the following arrangement, you can see that the dx square minus y square has very little interaction with the actual ligands. There is some interaction, mind you, but it's not too bad. The same thing can be said for the dc square orbital. The interactions are there, but they are not full-on direct interactions. Now, if you look at the dyz orbital, the interactions are actually a lot more prevalent than they were on the dx square minus y square or dc square orbitals. We see how the ligands here have a direct contact with some of the lobes of that orbital. Same thing can be said for the dxy orbital. You have direct interactions between the front and back ligands in regards to the lobes of this orbital. And when you look at the dxz orbital, the same thing happens with the front and back ligands. So you have some direct contact with those orbitals. It's not with all 4 of the lobes of the orbital, but there is some contact, making these 3 interactions worse in energy than the interactions with the dx square minus y square and the dc square orbitals. Alright, so altogether you have your 3 kinds of splitting, and you're kind of required to remember the pattern, right? So 3 on the bottom, 2 on top for the octahedral, 2 on the bottom, 3 on top for tetrahedral, 2, 1, 1, and 1 for the square planar structures. And as I said before, the separation between lower and upper energy levels or orbital levels is what we call the delta octahedral splitting, delta tetrahedral, and delta square planar, which for your reference, the value on the bottom has an energy associated with 0.4 delta octahedral values, negative 0.4. The top value is associated with 0.6 delta octahedral values. For the tetrahedral structure, the bottom one is associated with negative 2.67 delta octahedral values, and the top one with 0.178 delta octahedral. For the square planar, the bottommost energy levels have an energy of negative 0.514 delta octahedral values, negative 0.428 delta octahedral values, negative 0.228, and then you have the final one here, which is the largest energy, right? And you basically what you can see is that for whichever value of orbital you're dealing with, as long as it's negative, you're dealing with an attractive interaction. This is what allows the complex to bind. And if the value is positive, what that tells you is that you have a repulsive interaction among your electrons, right? So the potential energy is getting raised. Altogether, delta octahedral is roughly the same as delta square planar, and delta tetrahedral is 4/9 of delta octahedral. So it's actually a lot smaller than your delta octahedral splitting. Okay, so we'll stop right there and we'll continue in the next video by looking at trends.